Welcome to the video for Chapter 20. Today we're going to be talking about plane wave propagation, just as we did in Chapter 19, except today it won't be in free space, it'll be in a dielectric medium. Maybe it'd be more precise to say that it's in anything other than free space. We could be talking about transmission through an insulator, which would be a dielectric, transmission through a conductor, or transmission through something in between, something like a semiconductor. So obviously these are all very important things for electrical and computer engineers. We really need to understand how the wave changes when it moves from a vacuum or from free space or the air when it moves into a solid or liquid piece of material. So we're going to talk about how a dielectric medium affects the propagation of the electromagnetic plane wave. We're going to use the results of what's called the parallel wave experiment, which we'll talk about, to determine the relative dielectric constant of an unknown material. This is a very important experiment. We're also going to talk about the propagation constant, the phase constant, and the attenuation constant of a dielectric material. We're going to calculate the phase velocity of an electromagnetic wave in a dielectric medium. Actually, and also added in here, we're going to be calculating the characteristic impedance of a dielectric medium, and then calculate the skin depth of a dielectric material. Our historical perspective today, because we're going to be talking about how the velocity of a particle or velocity of a wave changes when it enters into a dielectric medium, I wanted to highlight a scientist whose work is really talking about how you can actually stop a beam of light. And they do this using something called a Bose-Einstein condensate. Professor Howe is a brilliant scientist, a strong candidate for a Nobel Prize someday. They've also found that they can convert light to matter and vice versa, which has applications in quantum encryption and quantum computing. It's a really exciting application of some of the things that we're talking about today. It's also the first time that we've had a historical perspective of a person who's still living, so that's exciting. Okay, so let's briefly talk about traveling waves. We haven't actually used that phrase before, traveling waves. I took an entire class, it was called Traveling Waves when I was an undergraduate student, but I just want you to recognize that the name of this equation that we've been talking about so far is a traveling wave. And it's traveling because it varies both in time and in space. And I just want you to remember that we've proven that is a solution to the wave equation, which is in alignment with Maxwell's equations, as long as this condition is met. And this is not a definition of what K is, it is a definition of what K must be in order for the traveling wave to obey Maxwell's equations. So just remember that K equals omega over C, or there are a dozen other varieties of that relationship that we can talk about that would be relevant. Notice, by the way, that as we're going to talk about today, omega is really dealing with the time variation of the wave, and K is really dealing with the spatial variation of the wave. And so when we're talking about the relationship of time variation with spatial variation, that's related through the speed of light, or through the speed of propagation within whatever material it is that we're looking at. Just wanted to remind you that when we're focusing on equation 20.1, it's actually very difficult to visualize that equation because it's varying in both time and space. And our brains do very well with studying one variable at a time. We can understand variation with time, we can understand variation with space, but when it varies in both at the same time, unless we're looking at an animation, it's very difficult for us to understand exactly what's going on there. So what we're going to do is we're going to try to look at this equation from two different perspectives. We're going to try to visualize this, first of all, thinking about time variation. So what I want you to picture is that we're going to sit at a particular point in space, maybe z equals 0, maybe z equals 100, but we're going to sit there and we're going to watch the waves going past us, sort of like sitting on a beach and watching the waves as they roll up onto the shore. We're not moving in space at all, we're only moving in time. We're waiting as time flows past us, and in order to fully characterize the wave, we would have to wait at that point forever. Obviously, we're not going to do that, but you can picture an experiment in which that would be the case. So here we're really focusing on the time perspective, the time variation of the wave, and in that case there are three variables that make a difference to us. There's the frequency f, there's the radial frequency omega, and there's the period t. And I've got equation 20.2, which shows the relationship amongst all of those. Remember that the period t is the time between when one peak of the wave hits our point of interest to the time when the next peak of the wave hits our point of interest. 1 over t is the frequency, multiply the frequency, which is the revolutions per second, by 2 pi, and we get radians per second, and that's omega. Typically, omega is the most useful of these when we're working with equations, but it's also the hardest of them to recognize. It's the hardest one to see. We can actually directly observe the period. That can be observed and then typically we're going to need to calculate omega from observing t, or I guess you could observe f if you had the right equipment. So if we come back up to equation 20.1 and realize that if z is a constant, and let's for simplicity, let's just say z equals 0, well then that term would go away, and we're left with just e sub 0 cosine of omega t. And I'm going to erase that because it isn't always going to be that way, but that takes us down to equation 20.3. Remember that's the equation if we're going to sit at a particular point in space and watch as the wave flows past us. And that is what's shown here. So you can see that as the sinusoidal wave, it's time harmonic, so as it's flowing past us, we're seeing a smooth sinusoid in space. We've specified here the point at which we're looking, and we've specified the period of this wave. And as a matter of fact, you can see that, let's see, if I start here at t equals 2 seconds, and I go one complete cycle, I'll end up here. That's at t equals 3 seconds, and so we verified, in fact, that the period is 1 second. From that, we could calculate the frequency, and from that, we could calculate the radial frequency. Now conversely, we could, rather than sitting at one point in time and watching for all of time, we could take a snapshot in time, a particular moment in time, and look at the full length of the wave. We could look at all of space. Again, not physically possible, but you can imagine it. So in this case, there are only two variables that are relevant to us. There is the wave number k and the wavelength lambda. Again, we can measure lambda directly from the wave, and then this is the most useful one, but we're going to need to calculate k. And of course, equation 20.1, if we eliminate omega times t, if we just choose t equals 0, say as the moment of our snapshot, then that would reduce down to e sub 0 cosine of kz. Remember that equation and this figure, which follows right here, is we're taking a snapshot in time, but we're looking at all of space. So notice that down here, the x-axis is z in meters. We're taking a snapshot at t equals 0, and this says that lambda is 1 meter. Again, we can pick any point that we want. I'll take 1 meter here. I'll do a full cycle. I'll get to here. That's at 2 meters. So in fact, we do see that lambda equals 1 meter. Just as up here, when we did this calculation, we saw that the period, capital T, is 1 second. So if those two figures look very similar to each other, they are, and that's actually one of the main causes of confusion, is that if I didn't take all of this time to talk about the difference in a time perspective versus a spatial perspective, the two figures look identical, and they're not. They are identical in appearance, but they are not at all identical in significance or in meaning. And so that's one of the reasons why traveling waves can be kind of confusing to us. In particular, then, what we want to do is we want to understand the relationship between the radial frequency omega and the wave number k. And I just want to remind you that we have cosine of omega t plus or minus k times z. So notice that omega and k fill a very similar role here. They are both right where the rubber meets the road. They are inside of the cosine. Yes, there's other variables that are floating around out there, but omega and k are the gold standard. They are the two most important variables, and they are analogous to each other. Neither can be quickly identified from the figure, but both appear quite clearly in that equation. So I want you to sort of be aware of omega and k there. I also want you to be aware that let me scroll all the way back up here to the top, the very first equation that we showed, remember that we had this one, equation 19.25. We said k equals omega over c. That was when we originally defined what k was even going to be as a thing. But let's rearrange that equation so that we can specify it in terms of the phase velocity, which remember in free space, the phase velocity is equal to c, but we're not in free space right now, so it's going to be something else, is equal to omega divided by k. So once again, we see this omega and k, these two peer variables that are similar to each other in a lot of ways. It's the ratio of those two that define the phase velocity that we need to work with. Alternatively, we could say lambda over t. Those are, again, two similar variables. Both can be easily observed from the figure, and if you had lambda and t, you could quickly calculate the phase velocity. In free space, we know that v sub phi is equal to c, but that will not be the case in our variable in our systems here, so I'm going to go ahead and erase that here. Okay, we have a wave that's traveling in free space that has a wavelength of 2 meters. As a matter of fact, this relationship between wavelength and And frequency is so common that when you hear somebody talking in radio transmissions, they'll often refer to something as, oh, I'm transmitting it at 3 meters. They won't even talk about the frequency, which is, up in the hundreds of megahertz, but they'll talk about the wavelength. So I just want you to sort of be aware that this idea of talking about wavelength is actually very relevant when we're doing these transmissions. So I want you to determine the radio frequency, the wave number, and the period, and I'm going to do those in a slightly different order because it's easiest to calculate the period t. T is going to be equal to lambda divided by c, and it does say that it's in free space here. We aren't yet in the world of dielectric materials. So this is going to be 2 meters divided by, well, I kind of have a habit of not writing the units here as long as they're all consistent SI units. So 2 divided by 3 times 10 to the 8th is going to give me 6.67 nanoseconds. 6.67 times 10 to the minus 9th seconds. We can then calculate omega. Omega is going to be 2 pi times f, which is 2 pi divided by t. So 2 pi divided by the period. That's going to give me 2 pi over 6.67. That's kind of hard to read. Let me try to get that a little bit better. 6.67 times 10 to the minus 9th. And that works out to be 9.42 times 10 to the 8th radians per second. So this is a relatively short wavelength, and therefore it is a relatively high frequency. When we talk about frequencies, we're often going to be talking about 10 to the 8th, 10 to the 9th, even 10 to the 10th. And then the wave number k, we can calculate that as omega divided by c. If all of these variables and all of these equations are kind of confusing to you, remember that in chapter 19, there's that sort of hexagram figure that allows you to do any of these conversions and find the variables that go between them. So this is going to be equal to 9.42 times 10 to the 8th radians per second divided by 3 times 10 to the 8th meters per second, which gives me 3.14 meters to the minus 1, which you'll sometimes see written as radians per meter. So again, just a refresher of how to do the relationships amongst these variables. If you feel that I'm over talking on this, if you feel that we're spending way too much time emphasizing the difference between a spatial perspective and the time perspective, I understand that, and I know that we are taking a lot of time to talk about this, but it's something that I didn't understand until I was a professor. I was a very good student, but I didn't understand this, and so I'm really trying to give you this perspective because the thing we're about to dive into will really be helped if you understand these two different ways of looking at the wave. The reason for that is because when we go into dielectric materials, we're going to find that the wave number is going to change. So when we get into the dielectric material, I want you to remember that in free space, the k sub 0, the wave number in free space, is 2 pi f divided by c, which is 2 pi f times the square root of epsilon 0 times mu sub 0. Because remember that c is 1 over the square root of epsilon 0 mu sub 0. So having the c in the denominator flips that up into the numerator. So that's equation 20.7. I'm going to try to squeeze equation 20.8 onto the screen at the same time, because what happens when we go into a dielectric material, the epsilon 0 becomes epsilon 0 times epsilon r, and the mu sub 0 becomes mu sub r times mu sub 0. Now, in practice, what we're going to find is that the mu sub r is equal to 1. Unless this happens to be a ferromagnetic material, which would be very unusual, we're going to find that most of the time, if we're transmitting electromagnetic waves, mu sub r is going to be equal to 1. So what we find, and I actually don't put this equation until the very end, is that k is equal to k sub 0 times the square root of epsilon r. That's a good equation for you to have in your notes. Because if you look back up here at equation 20.7, there's a 2 pi f, and in 20.8 there's a 2 pi f. In 20.7 there's a square root of epsilon 0 mu sub 0, and in 20.8 there's a square root of epsilon 0 mu sub 0. The only thing that's different is the square root of epsilon r. Now epsilon r must always be greater than or equal to 0. So epsilon r is always greater than or equal to, I said 0. It's greater than or equal to 1. And so therefore we know that k is going to be increasing. So as epsilon r increases, k is also going to increase. So the wave number in a dielectric material will be higher than the wave number in free space. Now the most interesting thing about this situation is that the rate of time variation does not change. So in other words, omega is constant. Again, if we look at it from the spatial perspective, k is increasing. If we look at it from the time perspective, it is not changing. Omega is going to be a constant. So if you remember, let me try to scroll back up here. We have a relationship. V sub phi is equal to omega over k. So I'm going to copy that back down here again where it's relevant. So V sub phi is equal to omega over k. And remember that since k is in the denominator, if k increases, then V sub phi must decrease. So what we find is that as epsilon r increases, k increases, and V sub phi decreases. Now that makes sense, because if V sub phi is going to change, if it's going to be anything other than c, it has to get lower. It can't go higher. Nothing will ever be faster than the speed of light in a vacuum, 3 times 10 to the 8th meters per second. Nothing, nothing, nothing. And if anybody ever gives you a number where the velocity is higher than that, they've made a mistake. So we know that if V sub phi is going to change, it will be decreasing. And it will, in fact, as a matter of fact, we can say that V sub phi is equal to c divided by the square root of epsilon r. So we have this equation here that shows how k changes, and we have this equation here that shows how the velocity changes. Notice then I can show you a picture, and this is a picture that I generated in MATLAB, which if you have a wave here that has a wavelength of 2.5 meters, so it starts out at 0 here, and then 2.5 meters later it's completed one cycle, and then at 2.5 meters the material changes, so that the wavelength is now, so the material is now glass instead of air. And you'll notice that over here the wavelength was 2.5 meters, over here the wavelength is 1.25 meters, and so if we come over here to where the first cycle has been completed, that's between 2.5 and 3.75. Sure enough, that's a 1.25 meter wavelength. So just realize that as we go from air into another material, let's say glass or any other sort of dielectric material, the wavelength is going to shrink because the wave number is increasing. So I should add that up here to my list of things that are changing. As epsilon r increases, k will increase, V sub phi will decrease, and lambda will also decrease because lambda and k have an inverse relationship. So the most important thing to me is not that you understand how to use these equations. We're going to see some big old equations today, but I want you to understand the physical significance of what's going on. I want you to see what is happening as we transition from air into glass or into some other dielectric material. So here's a question. What is the relative dielectric constant epsilon r for the glass that's shown in that figure? You know, we just showed a change in the wavelength, but what is the change in the dielectric material? Or, I'm sorry, what is the change in the dielectric constant? We know that over here, because this is air, and we can approximate air as a vacuum, epsilon r is equal to 1. But what about on the right-hand side? So let's consider, first of all, we're going to look at air. So in the air, we know that k sub 0 is equal to 2 pi divided by lambda sub 0. And the 0 subscript there is referring to free space or air. And then let's consider glass. So in glass, we know that k is equal to k sub 0 times the square root of epsilon r. So we can actually solve that equation for epsilon r. Epsilon r, which would be the epsilon r of glass, of course, is equal to k divided by k sub 0, the quantity squared. Well, k in the glass is 2 pi divided by lambda, and k sub 0 is 2 pi over lambda 0, and that quantity is squared. Now, each of those has 2 pi that can cancel. The lambdas are in the denominator, so the denominator of the numerator becomes the denominator, and the denominator of the denominator becomes the numerator. They both flip. So this becomes lambda sub 0 over lambda, the quantity squared. And that is 2.5 meters divided by 1.25 meters, the quantity squared, which is 2 squared, which is 4. So the relative dielectric constant of glass in this example, it might be a special type of glass, is equal to 4. So if you have a relative dielectric constant of 4, it will lead to a doubling of the wave number, a halving of the wavelength, and therefore it would also decrease the velocity of propagation by a factor of 2 as well. It would go from 3 times 10 to the 8th down to 1.5 times 10 to the 8th. Now, it appears that the wave is changing more quickly in the glass. This is something that was very confusing to me, is that in the glass over here, you can see this part of the wave looks to be moving more quickly than that part of the wave. But it's actually misleading. That's actually not the case. In reality, what we're going to find is that although this wave is changing twice as rapidly in space, remember that each one of these, so this interval here is going to take one time period t to move that far, because the time evolution is in lockstep with the spatial evolution. And now this interval here is also going to be one time period, and then this interval here will also be one time period. So if you look in the blue region there, of course the wave is moving twice as far over the same period of time as compared to the yellow region, where it's moving half as far in the same period of time. That's why we say that the velocity in the yellow region, which we'll call v sub phi, is equal to c divided by 2. So that was something that, again, was a little bit confusing for me when I was a student. I just wanted to highlight the reason why the velocity is actually half as much in glass as it is in the air. Oh, and here we're actually calculating those, which I kind of mentioned to you earlier. Well, in air, of course, c is equal to 3 times 10 to the 8th meters per second. And in the glass, we're going to find that v sub phi is equal to c over the square root of epsilon r, which is c over the square root of 4, which is 1.5 times 10 to the 8th meters per second. Okay, so now we understand that as we enter into a dielectric material, the velocity is going to slow down, the waves are going to become more compact, the wavelength is going to shrink, the wave number is going to increase. All of those things are going to happen as we move into a material that has a dielectric constant epsilon r that's different than free space. How can we use that to our advantage? We're going to do something called the parallel wave experiment. We're going to use the parallel wave experiment to determine the relative dielectric constant of an unknown material. So typically what we're going to do is we're going to take an electromagnetic wave, such as a beam of light. We're going to split it into 2 beams of light. We're going to send those 2 beams of light through 2 different materials. Now, quite often, one of those materials is air or vacuum, and then the other material is going to be some sort of unknown material. So we have a light source over here, and I'm going to draw this like a cartoon. So there's a light bulb, and we're going to send their beams here. That's going to go in through some sort of a splitter, and that splitter is now going to be sending 2 parallel beams of light, and each of them is going to pass through a length of material. So here you can see we have 2 different materials, but they have the same length, and then it's going to come out here into some sort of detector unit that's going to look at both of them. So the question is, what would happen as the wave is progressing through those two regions? We understand that if, let's say that this one is air, well, we understand that it's going to propagate through air, just as we would expect. And then if it's passing through another material that is not air, we know that the waves are going to become compressed by the dielectric material. And I'm going to exaggerate that here. I'm going to exaggerate it by showing that the wave is changing much more quickly. And what we're going to find then is that the phase difference at the output can be used to determine the epsilon r of the unknown material. Now, as I mentioned, I really exaggerated that difference because what we're going to find is that we can detect maybe tenths of a percent or even hundredths of a percent of difference in the dielectric constant by using this parallel wave experiment. So let's first of all consider we have equations for K in both of the 2 materials, and the only thing that's different on the right hand side is this epsilon R1 and epsilon R2. So that leads to the K1 and the K2. Here's actually a MATLAB plot that I used to show in the top, in the blue, I have a wave that has a wavelength of 1.00 meters, and on the bottom, I have a wavelength that is 1.02 meters. So it's only off by 2%. And notice that the waves start perfectly in sync, perfectly in phase over here on the left. That's where you have the source, and we split the wave, and it's going in here. It's going into both of these 2 in parallel, and then it hits the 2 materials. Now you'll notice that when you get to here, they're pretty well still in phase. One cycle later, oh, that one's a little bit out of phase. Another cycle later, this one's even more out of phase. Another cycle later, we're significantly out of phase. And then one more cycle later, look how far out of phase we've gotten. So just by having a little tiny difference in the wavelength over several cycles of the wave, over several wavelengths of the wave, that phase difference adds up. And so, again, this is actually exaggerated. 2% difference would be extraordinarily large, and that would mean that we were only perhaps getting it to within 2% precision. But in reality, we can do quite a bit better than that. So we can use a modern oscilloscope to detect a phase difference of 1% or maybe even tenths of a percent. So a very tiny phase difference can make the difference. And if you were really trying to characterize this material, you wouldn't have 5 wavelengths, or here we have 1, 2, 3, 4, 5 wavelengths. We wouldn't do that. We would have 500 wavelengths, or at least 50 wavelengths, so as to be able to really amplify the effect of the phase difference. So let's do some math here. We understand what's going on, but we want to really have an equation that can characterize this mathematically. So we know that the phase difference, which might be 1 degree, 2 degrees, 3 degrees, something like that, that's going to be equal to phi sub 1 minus phi sub 2. Phi, the wave phase in the first material, minus the phase in the second material. And the phase in the first material is K1 delta Z, and the phase in the second material is K2 delta Z. Well, we had equations for K1 and K2, and so we've substituted those. So here you see 2 pi f times the square root times delta Z. Everything except the delta Z is part of K, and there's K1, and then there's a 2 pi f in the second term as well. So K1 times delta Z minus K2 times delta Z. Interestingly, because material, we'll say material number 1 is completely known, you can be either one of them. Whichever material is completely known, you can calculate the phase of that one. Because remember, if I'm looking just at phi sub 1, I know 2, I know pi, I know f, I know epsilon r1, which is typically 1, I know epsilon 0, I know mu sub 0, I know delta z. I know everything that I need to know to figure out the total phase of one of the two waves, and I also can calculate everything that I need to know except for one thing. I don't know epsilon r2 in the phase difference. The only unknown in that entire equation is going to be epsilon r2. Well, it turns out that the 2 and the pi and the f will cancel. And interestingly, the delta z also cancels. So we end up with, and then there's a square root of epsilon 0 and a square root of mu sub 0, square root of epsilon 0, square root of mu sub 0. We end up with 1 minus, and this probably deserved a box, 1 minus the square root of epsilon r2 divided by the square root of epsilon r1. So if we know the percentage difference between the phase of the two signals, and if we know epsilon r for one of the materials, we can determine epsilon r for the other material as well. So let's see an example of this. I know that the parallel wave experiment has one material with a vacuum and the other material is unknown. The length of both tubes is 1 meter. The phase of the unknown material is 3 degrees different from the signal in the vacuum. And the frequency of both signals is 10 gigahertz. What is the relative dielectric constant of the unknown material? Okay, so let's say delta phi is equal to 2 pi f times the square root of epsilon 0 mu 0 times the square root of epsilon r1 minus the square root of epsilon r2, and then that's all multiplied by delta z. And I should say, I know that the delta phi is 3 degrees. And furthermore, because this is an equation where degrees is going to be compared to some other calculations, it must be in radians. So I know that 180 degrees is equal to pi radians. And so this is going to give me 0.0523 radians. So that's delta phi. Now if I solve this expression for epsilon r1, say. So let's say that I know epsilon r2 is going to be air, and I want to calculate epsilon r1. Well, then epsilon r1 is going to be equal to, and here we have delta phi. Maybe don't write this until I finish this entire equation, because I'm going to make a change. Divided by 2 pi f times delta z, and then in the denominator we also have an epsilon 0 mu 0, and then that's going to be plus the square root of epsilon r2, and then that quantity is going to be squared. But this right here is going to be a real hassle. I'm going to end up with the square root of 8.854 times 10 to the minus 12th times 1.2566 times 10 to the minus 6th. But remember that c is equal to 1 over the square root of mu sub 0 epsilon 0. And so I can take this and instead have c up in the numerator and erase this square root from the denominator, and it makes my life an awful lot easier because c is an easy number to work with. So let's go ahead and plug this in. So we know that this is going to be 0.0523, that's delta phi in radians, must be in radians, times 3 times 10 to the 8th, that's c, divided by 2 pi times f. F is 10 times 10 to the 9th, because it's 10 gigahertz. And then times delta z, which was 1 meter, and then that's going to be plus the square root of epsilon r2, which is just the square root of 1. That quantity squared gives me 1.0005. And so if you think about it, that would be 0.05% different than 1. And we can tell that difference over the course of just 1 meter of work. Now let's just double check this. That was a pretty intensive calculation, so I'd like to make sure that I didn't make a mathematical error. I know delta phi is a quantity that I know. That's equal to 2 pi. Remember that that's this equation up here, so I'm basically double checking with that equation. 2 pi times f, which is 10 times 10 to the 9th, divided by c, because again I'm going to take the square root of mu sub 0 epsilon 0. It was in the numerator, so c is going to move down to the denominator, which is, oh, I shouldn't just write c. It's 3 times 10 to the 8th, and then that's going to be times the square root of 1.0005 minus the square root of 1. And then that's times delta z. And if I plug all of that into my calculator, I get 0.0523 radians. And that's the same thing we got up here, but I just want to go ahead and convert it back into degrees so I can compare it to the original problem statement. 180 degrees divided by pi radians is going to give me 3.000 degrees. So I'm feeling good about the fact that I did in fact get the 3 degree difference back when I plugged in 1.0005. Okay, so far we've talked about what happens when the wave goes into a dielectric material. We've also seen how we can apply this, how we can use that to our advantage in the parallel wave experiment to calculate what is the dielectric constant of an unknown material. Now we're gonna take this one step further. Because remember, we've really been talking about perfect insulators here. Looks like I have a missing closing parentheses there. We've only considered the propagation of plane waves in free space or in a perfect dielectric material. In other words, in a perfect insulator. But there's no such thing as a perfect insulator. Every insulator has some level of conductivity. So the question is, what effect does the conductivity of a material have? And the short answer, without even doing any math, conductivity means that there are free electrons. Free electrons will always react to electromagnetic waves. And according to Lenz's law, those reactions will always be such that they diminish or cancel the electromagnetic waves. So even before we do any math, we can tell that conductivity is going to cause electromagnetic waves to sinusoidally decay. They won't stop oscillating, but they're in their death throes. As they're oscillating, it's the last few oscillations before they eventually decay down to nothing. We actually already saw this in section 17.4. Right after we derived the wave equation, we saw that even before the wave equation, when we just derived Maxwell's equations, we saw that the magnetic wave applied to the surface of a conductor has what we call a sken depth, and that was a measure of how far the wave penetrates into the conducting material before it substantially decays. That was when we figured out why you can't cook a frozen turkey in a microwave oven. We have studied wave propagation in the insulator. That's the last two sections that we just finished talking about. And we talked about them in a conductor. That was section 17.4. So if you think of there being a spectrum, we're over here, we say that sigma is equal to 0. That's an insulator. And over here, sigma is approaching infinity. That's a conductor. So here we have a conductor, here we have an insulator, but there's this whole region in between. There's this whole spectrum in between that we don't know anything about. We understand how to handle an insulator, we understand how to handle a conductor, but there's this whole area called semiconductors that we might be, in this region right here. We really need to know what's going on in the middle there. So we need to do one more pass through this derivation to figure out, can we find a general solution? Spoiler alert, yes we can, but it's really hard. So for the first time in today's lesson, I'm going to kind of skim over the derivation a little bit. I'm going to just say, okay, there are some steps that we can do, but I'm not going to show you all of the steps because frankly it's very similar to the things we've already seen, and the parts that aren't similar are very tedious. We begin to talk about a lot of complex arithmetic and it becomes very tedious. So I want to prepare you for the fact that we're going to skim a little bit, but then we're going to really apply the heck out of it at the end. So I just want to remind you that from chapter 18, we saw the phasor form of Ampere's law and Faraday's law, Ampere's law, and Ohm's law. And we saw that this was in the case of a time harmonic plane wave. Furthermore, we saw that if we solve equation 18.20 up here for H, we actually did this part of it. We substituted that in, so we solved this one for H. We substituted that in here. And we ended up with the curl, I don't know if you remember this, the curl of E on the left-hand side, and that became a Laplacian of E minus, and I think it was the gradient of the divergence of E, and we said we're going to choose the Coulomb gauge, and that's going to make that term go to 0, so that the left-hand side is just the Laplacian of E. Then we're going to substitute equation 18.26 for J of R, because this J of R is actually J sub C of R. So that's actually the conductivity current, and then the conduction current. And we're going to simplify the right-hand side, and ultimately we end up with equation 20.6. So again, about a half a page of algebra is omitted there, but this gives you an idea of the steps that were followed to end up with equation 20.16. We're then going to further assume that the wave is only polarized in the y direction, so that this vector equation will reduce down to a simple simpler second order differential equation. And if we then take this constant here, and we've actually kind of done this before, if we refer to that as gamma squared. So I've got whoops, not the negative sign. Everything except for the negative sign goes into gamma squared. And so I've got 20.18 as the definition of gamma squared. Then, of course, equation 20.17 will reduce down to this form right here. And that was known as the one-dimensional Helmholtz equation, which has very clear solutions. We are aware of these solutions, and they are essentially a decaying sinusoidally decaying, let me try that again, exponentially decaying sinusoid. There we go. This gamma, we didn't give it a name the first time that we saw it, but it is known as the propagation constant. And the propagation constant has a real part and it has an imaginary part. You know, you look up here and there's an imaginary number there, there's an imaginary number there, but there's also real numbers floating around, and so it's going to have both a real and an imaginary part. We're going to refer to alpha as the attenuation constant, and we're going to refer to beta as the phase constant. So alpha is a description of how quickly does the wave decay. So you can see that the alpha is what appears in the exponent of the exponential, and it's a negative exponential, so it's decaying. So if you, let me scroll back up here where I've got a little bit of free space. If you think about the wave, and it's going to be decaying sinusoidally, and it's going to be decaying exponentially while it is also oscillating sinusoidally. This envelope here is controlled by alpha, and this rate of oscillation here is going to be controlled by beta. So we can have the real part, which is going to control how quickly the wave decays, and then beta, the imaginary part, is going to control how quickly it oscillates, because the beta appears right here in the cosine. So alpha is the attenuation constant, beta is the phase constant. And it's actually really difficult to solve for alpha and beta. I want you to come back up here and look at this equation, equation 20.18. Notice that there is a real part and there's an imaginary part. We have to take the square root, and then we have to separate the real part and the imaginary part. It takes pages of algebra, maybe a page and a half of algebra to do that. But when we do, and I'm skipping that part, when we do, we end up with these two equations here. We end up with an equation for alpha and an equation for beta. And yes, these are nasty equations, and yes, they're unpleasant to work with, but they are also the only completely general solutions for alpha and beta. And if you look at this, these are things that we know. We know the conductivity. We know mu. Remember that this is equal to mu sub 0 times mu sub r. We know epsilon, which is epsilon 0 times epsilon r. We know sigma. We know omega, and we know epsilon again. So we have a material that has some sort of conductivity. It's being we're applying a wave that has some frequency. It also has some sort of relative permittivity and relative permeability, mu sub r and epsilon r, and we can calculate alpha for a given frequency. We can do the same thing for beta. Notice, by the way, that both of these terms have this same square root in them, that this square root is identical in both of these, and we're going to be able to use that to our advantage here in just a couple of minutes. I just wanted to highlight that square root term for you. And we can also, we can go one step further, and that is we can say, what is the phase velocity? Well, we know that the phase velocity is omega divided by beta, because beta is the new k. Whoops, that's beta. Beta is the new k. Remember that k used to be a description of how quickly the wave oscillated in space. Now beta is the generalized version of k. So I would say beta is generalized k, where now we have other things going on than just that oscillation, but anytime that we used to talk about k, we can now use beta in its place. So omega divided by beta is really the same thing as omega divided by k, and if we do that calculation, we end up with equation 20.24. So I can find the velocity of any wave frequency, any frequency of wave. Interestingly, it will depend on the frequency. So we see that this is actually v sub phi as a function of omega. And that's important because it means that different frequencies of the wave will translate at different rates. So if you have a high frequency wave, it could go at a different rate than a low frequency wave. And if you think about what we often transmit as electrical and computer engineers, we would love to transmit lots of ones and zeros, right, with nice sharp corners. But if you did the Fourier transform, or the Fourier transform of that signal, you would find that there are a lot of frequency components, including some very high frequency components. And if those high frequency components are traveling at a different rate than the low frequency components, what we find then is that the output actually becomes curved. So it kind of does something like this. So yes, we're still getting the basic idea, but no longer does it have those nice sharp corners. And ultimately, you can imagine that if it translated far enough, it might wash it out entirely, and then we wouldn't be able to transmit the wave, or couldn't transmit the information. The wave would still be transmitting just different phases at different velocities. So that means that we could find that it effectively places a limit on the length of a transmission over a lossy medium, and every medium is lossy to one extent or another, and that leads to the need for occasional repeaters. Now, the frequency with which you're going to need repeaters will depend on the particular material that you're using. And if your material is good enough, it could be hundreds or thousands of miles between repeaters, but other times it could be much closer than that. And then finally, if we perform a similar analysis of the magnetic field, and then we take the ratio of the electric field to the magnetic field, we can find the characteristic impedance, which is also a function of omega. So notice that there we have an omega in the numerator, and then alpha and beta are also functions of omega in the denominator. So we're going to find that we end up with a lot of omega dependence in the calculation of the characteristic impedance. Okay, we have a 20 volt per meter plane wave, and it is oscillating at 900 megahertz, propagating in the positive z direction. The electric field is polarized in the positive x direction. The dielectric material has a relative permittivity of 10, which is epsilon r. It is non-ferromagnetic, so let me just make a note here. Epsilon r equals 10. You know what? I'm going to do it over here to the side because I'm going to be tight on space. Epsilon r equals 10, and because it's non-ferromagnetic, I know that mu sub r is equal to 1, and has a conductivity of 10 Siemens per meter. So conductivity is 10. And I guess at the very end, we're going to need to know that the magnitude of the electric field at the beginning is 20 volts per meter, and this is 10 Siemens per meter. We want to find out what is the full expression for the electric field as it decays inside the dielectric, and then also find the phase velocity and the characteristic impedance of the wave. So we're going to need to use those two big nasty equations for alpha and beta, and we'll have to also calculate some other things, but alpha and beta, alpha is, and you kind of have to go back and look at the equation because I don't want to write out the whole equation without the numbers, and then repeat it with the numbers. So I'm going to have 10, which is, that was sigma, that's the conductivity, times, and in the numerator here we're going to have mu, which is 1.2566 times 10 to the minus 6th. That's going to be divided by 2 pi times 10, that's epsilon r, times epsilon 0, 8.854 times 10 to the minus 12th. That's then multiplied by 1 plus and then it becomes the square root of 1 plus sigma, which is 10, divided by 5.65. Whoops, I forgot to do something. Omega. I need to know omega is 2 pi f. I know f is 900 times 10 to the 10 to the 6th. So this works out to be 2 pi times 900 times 10 to the 6th, which is 5.65 times 10 to the 9th radians per second. I needed that because I'm using it here in the denominator. 5.65 times 10 to the 9th, and then that's multiplied by 10 times 8.854 times 10 to the minus 12th. And I got to close that parentheses and square that term, close the square root, close the denominator, and then the outside square root. Now if I plug all of those into calculator, and actually I wrote a script in MATLAB to do this because I didn't want to have to do it with my calculator, I get 183.8. And if you do all of the units, you get 1 over meters. But we're going to have a special unit. You know how like there's volt amps, and there's volt amps reactive, and there's watts, and in reality the scientific units of all of those are the same, but by specifying a particular name we can specify sort of what the variable is. We have a new unit here called Napier's. It's named after a scientist named Napier. I don't think he's going to make it into the historical perspective. And so we're going to have Napiers per meter. Anytime that you see Napiers, I want you to think of attenuation. So Napiers are always talking about attenuation. Okay, we got beta. Beta is equal to 5.65 times 10 to the 9th times the square root of 1.256 times 10 to the negative 6th times 10 times 8.854 times 10 to the minus 12th, and then all of that is divided by 2, and then we have 1 plus the square root of 1 plus, and obviously if you were doing this by hand you could calculate that square root quantity one time and then use it twice. 1 plus, and this is going to have 10 divided by 5.65 times 10 to the 9th times 10 times 8.854 times 10 to the minus 12th. Close that denominator, close that square root, and then close this square root. And when we plug all of that into MATLAB, we get 193.3. And here we're going to use the units radians per meter. Or you could use meters to the minus 1, but because we're not using Napier's, we know that we're talking about just oscillations, not with decay. And so we can see that E, and we were told that it is polarized in the positive x direction. So this is E, you could call it E sub x, but I'm just going to do it with a unit vector at the end. E of z comma t is equal to, and the magnitude was the amplitude was 20 volts per meter, times the exponent e to the minus alpha times z. So this is e to the minus 183.8 times z, times the cosine of omega t, 5.65 times 10 to the 9th t, and we know that it's going in the positive z direction, so there's a negative sign here, minus k times z, but it's not k anymore, it's beta, and so we're going to get 193.3 times z, and then I have to specify the direction within which it is polarized, and it is polarized in the x direction, so that's a sub x, and then I have to specify the units. That's volts per meter, and that is a full description of what that wave looks like as it is dying, as it is decaying down to 0, and it's going to decay pretty quickly. It's going to decay over the course of just a few millimeters. And then finally, the phase velocity is omega divided by beta, which is, it turns out, 2.92 times 10 to the 7th meters per second. We were asked for that quantity. And then z sub c is j omega mu divided by alpha plus j beta, which is j times 5.65 times 10 to the 9th multiplied by times 1.2566 times 10 to the minus 6th. That's divided by alpha, which was 183.8, plus j times beta, which is 193.3. Again, MATLAB will come to our aid, and we get that it is 19.3 plus J 18.4 ohms. This idea of a complex impedance might have bothered you more if you hadn't already worked with complex impedances before. Turns out that this complex impedance is going to be extremely important to us. We will come back and spend quite a lot of time and develop an entire tool to work with complex impedance. Okay, so we've made a big deal. Let me scroll back up here again. Made a big deal about the fact that these equations handle the middle ground. They handle all of this territory in between insulators and conductors. We have a completely generic equation that can exist anywhere along the spectrum, all the way from insulators to conductors. But then it should also be able to handle insulators, and it should also be able to handle conductors. So let's consider taking these most general equations right here, and then the equation for the phase velocity, and then the equation for impedance. Let's take the limit of each of those as we have very low conductivity and as we have very high conductivity, and we should find that we get back the same equations that we had before. So I'm going to first of all take the case of the insulator. And in the insulator, I just want to notice that here we're taking the limit as sigma goes to 0. Sigma is the conductivity, so we're going to the place where conductivity is vanishingly small. That thing under the square root, remember how I said we'd be able to use that? Well, if sigma is going to 0, well, then that means that this term is going to go to 0, and it just becomes the square root of 1, which is just 1. So that makes our lives a lot easier. We can simplify the alpha equation and the beta equation quite a lot. Notice that we get, this is our expression for alpha, but since sigma is going to 0, if sigma is, so let's say this is small sigma, but if sigma goes all the way to 0, if it truly is a perfect insulator, then alpha is equal to 0. And that makes sense. Remember that if alpha is how quickly does something decay? Well, if you think about outer space is an excellent insulator. There are almost no free charges moving around in outer space. That means that light will decay extremely slowly, and if at all, as a matter of fact. So that the observation that light can travel, tens of millions of light years and still reach us undissipated tells us that in fact this actually is a reasonable calculation. The limit of b as sigma goes to 0 becomes omega times the square root of mu times epsilon, which is mu over the phase velocity, which is just equal to k. And so sure enough, as we go to the case of dielectrics where there is no exponential attenuation, we find that in fact b does go back to k. I'm sorry, beta does go back to k. So we can just work with k in the case of dielectrics. And of course, free space is an example of a dielectric. It's just a particular one in which epsilon r and mu sub r are both 1. The phase velocity, the limit as we take sigma going to 0, we get the equation that we'd already seen before. This equation right here. The only thing that I'll observe is that before these were mu sub 0 and epsilon 0. Now we have the possibility that there could be a dielectric constant. So there could be an epsilon r that could be changing the phase velocity to something other than C, even if we have a good insulator. And then the characteristic impedance is J omega mu divided by 0 plus J times K. And if we do a little bit of algebra and just step by step, we end up with the same expression that we had before, again, where these are not mu sub 0 and epsilon 0, they're mu and epsilon. So there's the possibility that it would be different than 377 ohms, but there's no decay. And that's the thing that I want you to take away from the case of the insulator. There's no decay, beta goes to k, and then phase velocity and characteristic impedance go back to the equations that we've already seen. Let's take the case of high conductivity. So now we have a conductor. We're taking the limit as sigma goes to infinity. And if we do that, then this term here becomes quite large. It means that the 1 becomes negligible. We end up with the square root of the square of sigma over omega epsilon, which is just sigma over omega epsilon. So again, we can use that to more easily calculate alpha and beta. And notice that alpha and beta actually take on the same value. This is actually something that we saw way back in chapter 17, but we derived it in a completely different and more specific way. But both of those equations, the one for alpha and the one for beta, in the limit as sigma goes to infinity, they both yield the same result. And so one measure of how good a conductor is how close are alpha and beta. Let's scroll back up to that example that we did earlier and notice that alpha and beta were pretty close to each other. We had an alpha of 183.8 and a beta of 193.3. They're pretty close, so it's probably a pretty good conductor. Down here, we're seeing now that if we do in fact have sigma going to infinity, well, so these are in the case of large sigma. But if sigma truly does go to infinity, then each of those two expressions will go to infinity as well. So we do see that ultimately alpha would go to infinity and beta would go to infinity. And what that really means is that if you have a wave, and over here, let's imagine that this is a superconductor. So here, the conductivity is going to go toward infinity. So if the conductivity goes to infinity and the wave is coming in and the wave hits, boom, it just dies right there. Absolutely none of the wave can penetrate in because the exponential decay occurs instantaneously. The phase velocity works out to be 2 omega, or the square root of 2 omega over mu times sigma. And because sigma is going to infinity, that also goes to 0. So that actually makes sense, that the wave is not propagating because there is no wave left to propagate. And then the characteristic impedance also goes to 0. Ultimately, there's a lot of algebra here, but ultimately, because there is a sigma that goes to infinity here, and as it goes to infinity, then this is going to go to 0. And so we're left with a knowledge of alpha and beta that matches our previous calculations, and v sub phi and z sub c, which we hadn't calculated before, but which gave us, reasonable results. Then I just want to remind you that there was also this thing called the skin depth, and the skin depth is a measure of how far a signal will penetrate into a material. And typically we refer to it as penetrating into a conductor, but you can have a skin depth that could be miles long. You could have a skin depth of 1,000 miles if you had an excellent dielectric. It just probably we wouldn't refer to it as a skin depth in that case. But the skin depth is defined as 1 over alpha for all materials. Now I know that there were like 12 equations floating around there, but I think that if I put them in this table, it helps to see those equations better. Notice that the middle column here is the general case, and so that's the big nasty equations. And in the far left, we have the insulator case as the conductivity goes to 0. The rightmost column is as the conductivity goes to infinity. And so I just wanted to summarize this all in one table here. This is kind of a really important key takeaway from today, and a good place for you to start anytime that you're trying to solve one of these problems. So to wrap things up, we need to understand traveling waves. We're going to be working with traveling waves essentially for the rest of the semester. We can either stay at one point and watch as the wave moves past, or we can take a snapshot of all of space at a single instant in time. When an electromagnetic wave propagates through a dielectric, its wave number increases, its radio frequency is unchanged, and its phase velocity decreases. So you can see here why the wave number increases, because epsilon r is greater than or equal to 1. So therefore k must be greater than or equal to k sub 0, and then v sub phi must be less than or equal to c. Let me just take a minute and say, anytime that I calculate a phase velocity, I always think to myself, is this greater than the speed of light? Is this number that I just wrote down greater than 3 times 10 to the 8th meters per second? And if it is, I know that I've made a mistake. I go back and try to find my mistake. Let's imagine that I'm taking an exam and I don't have time to find the mistake. I at least write a note to the professor that says, hey, I recognize that this is not possible. I've made a mistake, but I want you to know that I know that the speed of light can never be higher than 3 times 10 to the 8th meters per second. So just be aware of that. Parallel wave experiment, we have a couple of equations, but this one can be used to quickly and easily calculate the relative dielectric constant of an unknown material. If we apply a time harmonic electromagnetic wave, a traveling wave, to a material that has non-zero conductivity, then it will decay as it's also oscillating. Alpha is the attenuation constant, beta is the phase constant. Although we don't typically refer to it, we do have gamma. Gamma is alpha plus j beta, and that's the propagation constant. Those constants, along with phase velocity and characteristic impedance, can be calculated for a general case, not necessarily an insulator, not necessarily a conductor, and then those general equations do in fact reduce down to the known quantities and the limits of low conductivity for an insulator and high conductivity for a conductor, and those results are summarized in this table right here.